Okay, so, basically, I have an exam in the morning, and I can't sleep, and I don't know, I think about math all the time at this point. I actually, I emailed myself of the homework I've been working on, just so that I can show kind of like where my headspace is at. This was problem 3, and then this is all my work for it on this page. Um, so yeah, basically, I want to do what I can to like share my understanding, um, and everything with other people, and I'm gonna try to make this video so that Archer can watch it, and someone else even in my field maybe can watch it, and it's just an interesting like the way I interpret things. But what I'm going to do is I'm going to try to explain imaginary numbers. Not just like basically know as little math as possible. Usually you learn about imaginary numbers in high school. Um, and they're basically just like talked about as a solution to a problem. Uh, like we can't take the square root of a negative number, so we just kind of like throw I in there. Imaginary numbers are the square root of -1. Um, and the reason that they're called imaginary is because a square root, um, to solve this equation normally, like if I were to take the square root of 4, I would need to find some number that, when multiplied by itself, equals what's inside here. So in this case, it's 2, because 2 times itself, which is just 2, is equal to 4. So that's no longer true. But yeah, um, there is no number multiplied by itself that will equal any negative number, because a -1 times a -1 um, is equal to 1. Negatives kind of swing back around. Now, I think that's a good place to start for a lot of people, but I think it's really important to take the next step, which is to sort of talk about what imaginary numbers are actually doing in like our math. Because they're in math a lot. I know a lot of people probably won't use them necessarily, um, but they have to do with a lot of really important aspects of, even in like business, uh, like econ, things like that. There's a lot of equations that maybe have imaginary numbers and they're just solved in a way you don't have to see them. But basically, we can talk about the number line, starting at 0. That's usually referred to as the origin in math, because um, if we choose a arbitrary point in space, it's usually pretty easy to say that that point is like the start of everything. So if we have something here, and then we say, this is 1. If I have 2 fingers, I could say they're 1 distance apart. But I would have to choose one of them to kind of be 0, and then like go 1 away from it, and now I'm 1 away from this finger. So you kind of arbitrarily choose something. But let's just say this point, like literally this point right here, that is our origin. That is 0. And this is just the number line that 1, 2, 3, 4. It goes out forever. And then over here, -1, -2, -3. Um, Funnily enough, actually, this here was what people had for a very long time when it comes to numbers. And the concept of zero, even, like you may have heard, that was invented by the Mayans. That was not a thing that like existed. So you get into negative numbers. There was a lot of like pushback in math against these introductions, almost like like the Galileo story with the sun, the heliocentric model. But just for these numbers that we work with every day now. But basically, if we continue, we can expand out on this and add another axis, basically. So it's like we've jammed another number line through that point, that origin. Um, and if we say, like x and y, now we're on to like basic algebra, graphing, things like that. That's, I don't know, that's pretty standard, but I don't think I'm going to do that just for the sake of not thinking about it necessarily as like a graph of space yet. It's more just arbitrary, like conceptual thing. Just like when you're counting, if you have like 3 apples, that's not necessarily like there's not like an apple axis that you're counting down. You're just kind of arbitrarily moving. So we again have, oh, I messed it up. 1, 2, 3, -1, -2, -3. So within this framework, we can have values that are both like a 2 and a 1. They're just like different values on different axes. The important thing to think about is that the negative axis here is almost like you've taken this value and like rotated it around this point, the origin. And I think these other axes that people are probably somewhat familiar with the concept of like an x and a y, but if not, you could have something where this is time, like since you were born, like this could be 1 second, 2 second, or like 1 year, 2 year, 3 years, probably more reasonable. And then this could be like how many feet tall you are, So if I were to draw the graph again, I'm not going to number it just for the sake of time, but like I don't even want to think about negative. Before I was born, how tall was I? No. So let's say it starts here and it's gonna like go up, and then I imagine it probably straightens out, and maybe I shrink a little bit later. Um, but it's just like relating these two values. But you can move within just like if we isolate this again, you can make these two-dimensional movements that like require there to be more going on than just a straight line without having to have necessarily um like a relation. You're not actually traveling from here to here. It's just kind of like a reflection, even, you could say. So that is what like a negative number is. So if I have 3 and that I could say as like 3, and I'm gonna just put like positive and negative here. I'm gonna just add a subscript. Now this is totally for demonstration. I do not believe this is used anywhere. It's like completely made up. But I'm just gonna add this made up symbol under the 3 that denotes the direction the 3 is going in. So it's like positive along the number line. Now, if I multiply that by -1, then, and -1 here would be the same as like 1 in the negative direction, but I'm being super, I'm just being a little pretentious, I guess, to like over-explain that this is in the positive direction. When we multiply it by a negative number, which we generally already have a symbol for, then that becomes 3 in the negative direction. Almost like, yeah, you like rotate it around the origin. So this operation here of we're taking some number and kind of thinking about it as like the distance between these two things. And then when we multiply by -1, it's almost like we're saying, okay, take the same value and put it in the negative direction or the negative like line. So now, going to imaginary numbers, which was the point of all of this, imaginary numbers are just like this. They're mapped onto this this number line, basically. And they are always like 90 degrees with the number line, but they're a different kind of thing, sort of. They're almost like every number line you add, no matter what direction you put it in. The imaginary axis, here we'll just like draw an eye to show it's imaginary, will always be 90 degrees to it. And that's usually denoted with a little box like this to show, because squares always have 90-degree angles, so it's, yeah. It's almost like we're saying, hey, every time, just like they said at some point, there has always been a 0, like 1, 2, 3, 4, 5, the other way, we're going to call that 0, we're going to call that -1 when we keep going. Now we're saying, like, this halfway, through this rotation from positive to negative, is going to be imaginary. And that's not like the best name for it, but because all of this is kind of imaginary. But there's different names, but that's the most well-known one. So, I can't get into the full reasoning behind why it's kind of a rotation, because then you have to work through, like, technically the imaginary axis, is kind of this like radial thing emanating out. But that, all that to say, I think that might be a little bit too much. All that is to say, we're halfway. We've done this rotation, but we're not quite all the way to the negative axis yet. Now, interestingly enough, that description sounds a lot like what we needed before. We needed some number that when you multiply it by itself, it's equal to -1. So when we multiply by -1, I'll denote that in like blue here. If we multiply by -1, we go like this. And then if we multiply by -1 again, then we go back to the positive, right? But we've just imagined, you could say, a new kind of space here that we can kind of sit in when we multiply the first time. And then when you multiply I times I, using this equation where the square root of -1 is I, so this would be I squared. And I squared is equal to the square root of -1 squared. And these like go away, they cancel each other out, and we just get this -1. So that is like how when I multiply by -1, I rotate all the way to the negative plane. When I multiply by I rotate into like this I direction, this I line, and then when I multiply by I again, I come back. Now, I'm just going to touch on very briefly. This is pretty advanced math, but there is a famous equation that e to the I pi plus 1 is equal to 0, I think is the full equation. So for people who haven't taken pre-calc yet, I'm going to just translate this. In pre-calc, there's this thing called the radian. We're not going to worry about that. We're just going to say e to the I 180 degrees. That's what pi means if you speak weird math language. And 180 degrees is a half rotation. In like that's a pretty common notation for rotation. You break it up into degrees of like angles. So e to the I 180 degrees plus 1 is equal to 0. Now, that might seem a little weird, but again, just like translating, what this is really saying is a line, or like an arrow, the length of I is going to get rotated 180 degrees. Now, the length of I, the magnitude of I, is equal to 1, because magnitude is, well, this is a little bit complicated, but it's basically like x squared plus I squared. In this case, you can imagine if we're starting off here, when we rotate, we're gonna have a new arrow here, and that will have to be I tall. I think this might be a little bit too complicated of a explanation. But yeah, so this equation is basically saying I'm gonna make a line I long, rotate it 180 degrees to the left, because that's just in this like notation sort of, that's just what we've defined as going to the left, multiplying by -1. Technically, you could go either way, but when you do that, one more time, I'll draw these axes. This is 1, -1, I, -I. When you do that, when you rotate it 180 degrees, now we're at -1. And when we add 1, we're just going to like march this way 1, and we're back at 0, back at that origin. So that is, I would say, the basis for, like, on the fundamental level in like math or anything like that. This is what imaginary numbers are doing, basically. There's an interplay. They're encoding like half, and importantly, when you in between these, like as the arrow is moving, as it's here, it has a little bit of its positiveness left. You could drop it down at all these different locations and make make a little line that's just in the x direction, or the positive 1 direction. And eventually it would go into the negative direction, but it would be as if the arrow like kind of went from here to here. This drop down of the rotation kind of goes from right to left as you do that. Yeah, so I think I'll end it there. I'm sure people will have questions, and I have more of a like real world application view that has to do with like electricity a little bit that I want to talk about later. But good night, everybody, and I hope you enjoyed.